Hello, everyone. How are you guys doing today?
Fine, thanks.
Great, great. Um, any question, comments, concern, anything before we start?
Hello?
Yeah, Gibran.
I saw somebody in the chat asked if tomorrow is in person. I just need you to confirm that. Okay, thank you.
Yeah, I was thinking to do it in person tomorrow, but I think I should hold it online. Because I'm not feeling so great. And my professor told us that he got COVID. Uh, so there is a chance that his students will get that from him. And he didn't know it before we had our class a few days ago. So probably after hearing that, my mind was like kind of scared. So I'm feeling a little sick inside. So I was thinking probably I should hold it online in case if anything happens. I'll try to test it, but there's no guarantee, right? So do any of you object? If you want me to be in person, I'll do it in person. But personally, for everyone's safety, I think I should do it online. Yeah. Sometimes when we hear from others, our mind get affected fast than our body. So I think that is happening with me. So in case online is good, yeah, I was thinking the same thing. You guys are going to have your midterms, right, in other classes. So I'm going to have I'm going to give your exam back next week. So next week we don't have Monday class, but we have Wednesday and Friday. Midterm grade, I'm grading both of you. I mean, I'm teaching two classes. So I'm grading both of your exam at the same time. So one exam from one class, another exam from another class. And since I'm grading both of them simultaneously, so it's taking longer. But I'll put it up once I'm done with everyone. I did almost half for everyone for both classes. So I still need half more. But I'll email you or I'll post the announcement on Brightspace once I'm done posting the grades. And this will definitely be before Sunday or Monday. I should say inshallah. It means if God wills. So if God wills, I'll post the grade by Sunday or Monday. And Monday there is no school. Okay, everyone. Any question? Comments? Concern? Nothing?
Hello.
Yeah.
Sorry, I came in late. Do we have class tomorrow?
online. Same
Okay.
link, same everything.
All right. Thank you.
And I'm going to make an announcement on Brightspace for the people who are who will not be here. Okay, so we started 1.5 and my plan is to finish 1.5 today. Is someone texting me? Okay, I'll read. So my plan for today is to finish 1.5 and we have few topics left only. So I believe we'll be able to finish it. And I may need 5 more minutes extra to finish everything. Okay. So if I go a little bit more than 6:45, please bear with me. And anytime you don't hear anything from me or if you don't understand anything from me, please unmute yourself and ask question. Okay. So last class we did inverse function. And we said we can find inverse using reduced echelon form. So in order to find inverse using reduced echelon form, we write our matrix on one side and identity matrix on the other side, but on the same matrix. Then we apply row echelon form or reduced echelon form. Actually, we're supposed to use reduced echelon form. Once you apply reduced row echelon form, then our A matrix turn into identity matrix. So our goal is to convert A into identity. So in this process, whatever the identity matrix turn into, that result is the inverse. Now, if you're working with 2 by 2 matrix, then your identity will be 2 by 2 matrix. If you're using 3 by 3 matrix, your identity will be 3 by 3 matrix. That means in order to apply this method, we have to have a square matrix, the coefficient. If the coefficient matrix is not a square matrix, then we cannot find inverse. And then we did one example, 2 by 2. We converted A matrix into identity matrix in 3 steps. And then whatever we got, the result on the other side of the identity matrix is the inverse matrix. So for 2 by 2 matrix, it was not so bad. And for 3 by 3 or 4 by 4 or 5 by 5, it takes a little bit time. And 2 by 2, it's 2 by 2, so we have even an easier method of finding inverse. In the easier method, we did use determinant. Determinant is the difference of the diagonals. And you always have to do the right diagonal minus left diagonal. So if the 4 elements in the matrix is A, B, C, D, row wise, then we do 1 over determinant and we multiply that with a new matrix. We switch the position of A and D and we switch the sign for B and C. And then we multiply by 1 over determinant. Or in other words, we multiply every element, not multiply, we divide every element by the determinant and we get the inverse matrix. Then we tried one 3 by 3 and we got this answer. So I have another example, but I'm going to skip that. Instead, I'm going to start with a new example where we have solving matrix. So in our last section 1.4, we learned that we can convert system of equations into matrix equations. In order to do that, we convert the whole system of equations into two parts. One is the coefficient, one is the variable matrix, and one is the constant matrix. So here, the theorem says, if you have a system of if you have a matrix equation, AX equals B, means coefficient matrix times the variable matrix equals the constant matrix. Then we can solve for X easily, but we cannot divide by matrix. Matrix division is impossible. So instead, what we do is for AX equals B, in order to get rid of A, we can apply A inverse. But since A is on the left of X, so you have to apply A inverse on the left side on the X. So the matrix rule is if anytime you multiply one side by one matrix, then you have to multiply the other side by the same matrix on the same position. So on the left side, you're multiplying the first position. That means on the right side, you have to multiply the matrix on the first position. You cannot do B times A inverse. You have to do A inverse times B. So you're applying A inverse on both sides of the equation on the left of both sides. So A inverse and A, they cancel out, and we get identity matrix. So here identity matrix times A. So identity matrix times X equals A inverse times B. But identity matrix times any matrix is a matrix itself. So even though it's I times X, but still only X. So we have A inverse times B. In other words, we don't even have to write this identity matrix. Oops. We don't even have to write the identity matrix. We can simply cancel A with A inverse and you get the X. Let's say you have another situation where you have X A equals, let's say B or C. So in this case, you have your A matrix on the left of the X. So in order to get to the A matrix, you have to multiply on the right side, on the right position on both sides. You cannot multiply the left position. If you multiply the left position, then you cannot cancel A with A inverse. So A and A inverse, they have to be together next to one another. So when A is on the right, you have to apply your inverse matrix on the right. So you multiply both sides on the right by the inverse matrix. So they cancel out, and we get X equals C times the inverse matrix. So the position of the matrix where you're multiplying is extremely important. You must keep it in your mind always. Any questions so far?
Yeah, I
Shane?
just have a quick question about clarification. For the X, is that a scalar unit or is that a unknown set?
Variable.
It is a
X1, X2, X3, or whatever units, whatever variable you have. This is your
okay, it's
X
the variable
matrix.
matrix.
Mhm.
That's what the X is.
Yes.
All right, thank you.
For example, on the next example, the first example on the right page, we have 2x plus y equals 21, x plus y equals -4. They want us to solve the system of equations using the A inverse, and they gave us the inverse for us. So first step, convert this into AX equals B. Some people like small b, some people like big B, it doesn't matter. So our constant is 21 -4. We write it in place of B. Our variable here is X and Y. So we write X and Y column wise. And our A is the coefficient. We have coefficients 2, 1 on the first equation and 1 on the second equation. So that's how we get A for coefficient, X for the variable, and B for the constant matrix. And now in order to solve for B, we need to multiply both sides by A inverse. So we have AX equals B. To cancel the A matrix from the left side, we need to multiply by A inverse both sides on the left. So A inverse and A cancel out, we get the identity. So identity times X is the X. And on the right side, we have A inverse B. Now they gave us the inverse. 1, -1, row wise, and also column wise, row wise 1, -1, and then second row is -1, 2. And you're multiplying by the constant matrix, column wise 21, 4. Now all you have to do is multiply them. So this X matrix is X and Y. And when you multiply first row and the column. So 2 times 21 is 21. 4 times -1 is -4. And then you do the other way around. You go second row and then the column. So for second row, we have -1 times 21, which is -21, plus 4 times 2, which is 8.
I believe it's a -4, not a 4.
Is -4, right? Yeah. So it's +4. Thank you for catching that. 1, -1, -1, 2, 21, -4. So 21 times 1 is 21, -4 times -1 is +4. That gives us 25. And 21 times -1 is -21. -4 times 2 gives us -8. That gives us -31. Oh, wait, why is -31? It's 39. Come on. 21 and 8, 29. So we have our X is 25 and Y is -29. This is the solution of this matrix. Any question? Any question from anyone? Was anything unclear, confusing? Nothing? So the next one. We have 3 matrices. All of them are 2 by 2. And this time we have the equation given to us, and we have to solve for the variable matrix. The first one says, solve for X from XA plus C equals X. So A, X, C, all of these are matrices, not numbers, they're matrices. So the first one, XA plus C equals X. Just like algebra, we need all the X together so that we can factor it out. So you have 2 ways of doing it. Either subtract C from both sides and subtract X from both sides. So C goes to the other side and X comes to the left side. And then you take it out as a common factor. Or if you want to have your C positive, then subtract XA from both sides. It doesn't matter which method you follow, the answer will get same. So if you subtract XA from both sides, we get C on one side and x minus xa on the other side. And now like algebra, we can factor out x. So c equals, we factor the x out. And now my question is this. You have x matrix and you are factoring it out. In algebra, factoring out means division. So in matrix, so when you divide x by x, in algebra, we get 1. But here we are using algebra, but not on numbers. We are using algebra on matrix. So if you try to divide x by x, what do you get? Matrix division is impossible. But if you try to divide, we definitely cannot divide, right? So what do we get here? Does anybody know?
The identity matrix.
Good job. Even though we cannot divide, but we already learned that instead of division, we do inverse multiplication. So factoring out x, it means we are multiplying by the inverse. So as a result, the inverse and the original matrix cancel out. You get an identity matrix in place of x. And then you subtract A from your identity matrix. Now we have C equals X minus identity matrix minus A. Now, if you want to get this X alone, for algebra, we know we could simply divide I minus A. But here we cannot divide by I minus A. So what can we do to get the X alone? Any idea? Instead of division, what do you do in matrix?
Do you put x inverse on the left side?
You cannot do x inverse because x is what you are looking for. So you have to keep your x. Instead, you are going to inverse I minus A. But my question is, where do you multiply? On the left on the x or on the right of I minus A? Where exactly you have to multiply?
Right.
Good job. Yep. Ashif and Abigail, you both are correct. You have to multiply on the right, I minus A. So you have an equal sign. On the left, you have C. On the right, you have X times I minus A. So you have to multiply I minus A inverse on both sides of the equal sign on the right. So C times I minus A inverse, whole thing. And then X times I minus A times I minus A whole thing inverse on the right side. So I minus A and I minus A inverse cancel out. You have your X alone on one side, and on the right side, you have C times I minus A whole thing inverse. So we done solving for X. Now all you have to do is do all this multiplication and inverse, and we are done. So you have to do it step by step. Pamela says, start with the parentheses. So in the parentheses, we have I minus A. That means this is the first thing we need to find. I minus A. Maybe I should do it on the side. Let me do it on the side. I minus A. It means we have identity matrix minus our A matrix. So identity is 1, 0, 0, 1. And we are subtracting A matrix, which is 5, 3 row wise, 3, 2 second row. So when you subtract, it's 1 minus 5, which is negative 4. 0 minus 3 is negative 3. Again, 0 minus 3 on the second row, negative 3. And 1 minus 2 is negative 1. So this is I minus A. Then we need to find I minus A inverse. Now, if this is A, B, C, D, so negative 4 is A, negative 3 is B, negative 3 on the second row is C, negative 1 on the second row is D, then its inverse is 1 over AD minus BC, and then we switch the position of A and D. So D goes to the position of A goes in the position of D. And then for BC, we change the sign. So we get negative B and negative C. This is our inverse matrix. So AD in this case is negative 4 times negative 1. So we get 1 over positive 4, and we're subtracting the left diagonal, negative 3 times negative 3, which gives us positive 9. So we have simply 1 over 5. So 5 is the determinant, and you're multiplying by 1 over 5. Now, when you change the position A and D, A is negative 4, D is negative 1. So you get negative 1 in the A position and negative 4 in the D position. Then our B is negative 3, C is also negative 3. We have to change their sign. So B is positive 3, C is positive 3. And we keep that. Negative 1, 3, 3, negative 4. In other words, we have we have I minus A inverse, I minus A whole thing inverse is negative 1/5, 3/5, 3/5, negative 4/5. You don't have to multiply, and if you want, you can multiply. It's up to you. 1/5 is negative, right? Because it's 4 minus 9. So this is positive 1/5, negative 3/5, negative 3/5, positive 4/5. Thank you, Hylon. So we did I minus A first, then we found I minus A whole thing inverse next, and now the last thing is the multiplication. So here we go back. We have our C matrix is 4, negative 6, column wise, negative 2, 3, column wise. And we just found our I minus A whole thing inverse is 1/5, negative 3/5, row wise, negative 3/5, positive 4/5, row wise. So all we have to do is multiply them. When you multiply, we do first row and first column. So 4 times 1/5 is 4/5. And then we are adding negative 2 times negative 3/5, which is 6/5. 4 plus 6 is 10. So we get 10/5, which is 2. Next, we go the first row, but second column. And with the same thing, 4 times negative 3/5 is negative 12/5. Then we add -2 times 4/5, which is -8/5. -12 minus 8 is -20/5, which is -4. Our second one. Then we have second row, which is -6/3. We multiply the first column 1/5, -3/5. So -6 times 1/5 is -6/5. And we are adding 3 times -3/5, which is -9/5. -6, -9 gives us -15/5. That gives us -3. And then lastly, we have -6 times 3/5. So we get to multiply the last column. -6 times -3/5 gives us 18/5. Sorry, 18/5, not 15. 18/5. And we are adding 3 times 4/5, which is 12/5. So 18 plus 12 is 30. We have 30/5, which is 6. In other words, our x is 2, -4 row-wise, -3, 6 row-wise. So this is our variable matrix. Any question? Any comments? Concern? No. So here is B. B says solve for x from ax plus b equals cx. So not now, in your spare time, outside of the class, try to solve it. And its answer for B, row-wise, is -8/23, and then -11/23. Second row is -26/23, and -7/23. So instead of doing that, I'm going to do another example, which is C. Here it says solve for x from a minus bx equals cx, where we have A matrix is row-wise 1, 2, 3, 4. B matrix is row-wise 4, 3, 2, 1. And C matrix row-wise 1, 3, 2, 4. So from here, we have A minus bx equals cx. Now you can not subtract. You can, you can subtract cx from both sides and subtract a from both sides. Or we can simply add the bx on both sides. So everything is positive. We get A equals bx plus cx. And now this time we have x on the right side. So we have to factor out our x from the right side. You cannot do the factoring on the left side. You have to factor the factor the x out from the right side. As a result, you get b plus c on the left. So I should change the color. X on the right side. So you get b plus c on the left side. If you try x on the left and then b plus c, trust me, this is wrong. So if you try doing this in the exam, you're going to get 0, regardless of what you did. If you did everything else correct, but you did your equation wrong, everything else is wrong. So wherever your variable is, you have to factor out your variable from that position. In this example, our x is on the right and numbers are on the left. So you must factor out your x from the right, not from the left. So in the last example, we had xa. So x was first on the left side. So we factored out x on the left. But here, x is on the right side, so you have to factor x out from the right, not from the left. So we have a equals b plus cx. And now since your b plus c is on the left side, so you need to apply your inverse matrix on the left side, on both sides. So you cannot apply your matrix on the right side. You may think, well, let me do this. I'll take x on the left side. So we get a here on the left, and then I can apply b plus c inverse on right side on both sides. So they cancel out, you get x equals 8 times b plus c inverse. You may think this is correct, but this is definitely wrong. A times b is not b times a. Matrix multiplication is not commutative. So you cannot commute them. You cannot switch their position. Their position is very important. So b plus c inverse and b plus c cancel out, and we get x matrix equals b plus c inverse matrix times the A matrix. That means first we need to know what is b plus c, and then we're going to take the inverse, and then we're going to multiply by the A. So let me try doing it real quick. First we have b plus c. Our b is 4, 3, 2, 1 row-wise, and 1, 3, 2, 4 row-wise. So when we add b and c, we add 4 plus 1, which is 5, 3 plus 3, which is 6. So 5, 6 row-wise. Then we have second row for both matrices is 2, 1 and 2, 4. So 2 plus 2 is 4. 1 plus 4 is 5. So we have 4, 6 row-wise. Sorry, 5, 6 row-wise and 4, 5 second row. Next, we need to find its inverse. So b plus c inverse, it's 1 over the difference of the diagonals. So the right diagonal minus the left diagonal. Our right diagonal is 5 times 5, 25. And we're subtracting the left diagonal, 4 times 6, which is 24. So basically it's 1 over 1, which is simply 1. And now for the matrix, we switch the position A and D, and surprisingly, this is also, we have the same number, 5 and 5. And we change the sign for B and C. Our B is 6, C is 4. So when we change the sign, it's -6, -4. So when you multiply by 1, you get the same thing back. 5, -6 row-wise, -4, 5 row-wise. Did I make any mistakes so far? No? we found the inverse matrix, and now we need to multiply that by A on the right. So B plus C inverse times the A matrix. So B plus C whole thing inverse is 5 minus 6, -4, 5. And our A matrix is 1, 2 row wise, 3, 4 row wise. So when you multiply, let me see if I can fit it here. You have 5, -6 times 1, 3. So 5 times 1 is 5, minus 6 times 3 is 18. 5 minus 18 is -13. Then we have first row, second column. So 5, 2, and -6, 4. 5 times 2 is 10, minus 6 times 4 is 24. 10 minus 24 is -14. Then we go to the next row. We have -5, 4. We are multiplying the first row, first column, 1, 3. So -4 times 1 is -4. 5 times 3 is 15. -4 plus 15 is 11. And now lastly, we are multiplying the second column. So -4 times 2 is -8. Plus 4 times 5 is 20. -8 plus 20 is 12. So that tells us our X matrix, which is B plus C whole thing inverse times A, is -13, -14 row wise, 11, 12 row wise. So this is our final answer. One check. -13, -14, 11, 12. Yep. This time I got it. I didn't make any mistake. Any question? I'm going to give you one of these, definitely one of these in the exam. So you really need to know how to do them. And also I posted the homework. So try doing the homework for extra practice. Tomorrow we'll have an online class, Ashif. So I'm going to post the grades online on Brightspace. Not tomorrow, by Sunday, inshallah. No problem. So any question from anyone so far? No. The next example is saying, try solving the system of equations using inverse. And the system of equations this time they're giving us is 2x plus y plus z equals 21. X plus y minus 2z equals -24. So first step is convert them into the matrix equation ax equals b. So ax equals b. Our a is the coefficient. So this time we have coefficient 2, 1, 1. For the for the first equation. And second equation is 1, 1, -2. And we have variables x, y, z. So x, y, z equals our B matrix is 21 minus 4. Now my question is, can we solve this system of equations or this matrix equation using A inverse? No, why not? Good. A doesn't have an inverse. A inverse does not exist. Sorry, not S. Does not exist. Because it's not a square matrix. Because A is not square. So in order to even have the qualification to have an inverse, first requirement is it has to be square. Since A is not square, so we simply have to say it's not solvable, not possible. Not possible. So you cannot solve this system of equations using inverse. If you want to solve it, you have to use the row echelon form, reduced row echelon form. But they're not going to do it because they're not asking to do it here. They're saying solve it using inverse. So that's all you have to do. So maybe I'll put this in the exam just to test your knowledge about the inverse and the square. Yeah. Any question, comments, anything so far? No. Okay, next we have triangular matrices. So we have three types of triangular matrices. One is called upper triangular. It means we have a matrix that looks like a triangle and it has numbers on the upper side. And all the numbers below the diagonal is zero. Sorry, are zero. All the numbers below the diagonal are zero. Then we have lower triangular. It means below the diagonal, we have all the non-zero numbers, and above the diagonal, all the numbers are zero. So whatever triangle you have, the other side has to have zero. Lower triangle has zero on the upside, upper triangle has zero on the lower side. And then if any triangular matrix has all zeros on the diagonal, then you call them strictly upper or strictly lower. For example, if you have 0, 1, 2, and then 0, 0, 3, 0, 0, 0, this is strictly upper because our diagonal is 0 and all the numbers are above the diagonal. So it's strictly upper. Also, if you have 0, 1, 2, 0, 3, 4, no, this is 0. And then 0, 0, 4, no, 0, 0, 0. So on the diagonal, you have 0, and below the diagonal, we have numbers. So this is a lower triangle, and it's strictly lower because our diagonal has all the numbers 0. So if diagonal has 0, it's strictly, and if you have numbers or a combination of numbers in 0, then it's just upper or just lower. A triangular matrix doesn't have to be an upper or lower matrix doesn't have to be triangular. It may have different shape. For example, it may have trapezoid shape. So if you don't have a square matrix, then you're going to have something like trapezoid. For example, if you observe here, we have A, D, G, I in the first row, 0, B, E, H on the second row, 0, 0, C, F on the third row. So if you follow the shape of the numbers, it's not triangular, it's a trapezoid. So it's an upper trapezoid matrix. Similarly, if you have A11,0,0,0 on the first row, A21, A22,0,0 on the second row, A31, A32, A33,0 on the third row. Then if you follow the shape of the numbers A11, A22, A33, and then A21, 31, and 32, it gives you, here it looks like a triangle, but we cannot stop here. We have to go all the way here. But still it's triangle. Okay, whatever. You get the idea, right? It may have one part, it may have a weird triangle, or it may have a normal triangle, or it may have trapezoid shape. They may have different types of shapes. But here in this class, we are going to work with only strictly triangular, upper triangular or lower triangular. Now, a triangular matrix is invertible if and only if none of the entry in the diagonal is 0. For example, if you look at the first matrix 3 to 1 row-wise, 0 to 1 row-wise, 0, 0, 5 row-wise, its diagonal consists of 3, 2, and 5. All of these numbers are non-zero. So this example is a non-singular matrix. So this upper triangle is a non-singular upper triangle matrix. On the other hand, the second matrix is row-wise 1, 0, 0, 6, 0, 0, and 1, 4, 3. So if you look at the diagonal, it consists of 1, 0, and 3. Since we have a 0 on the diagonal, so because of this 0, this is a singular, means this is a bad matrix. It's a singular lower triangle matrix. The left one was upper triangular, non-singular, means it's a good upper triangular matrix. The second example is a lower triangular, and it's singular, means it's a bad lower triangle matrix. And then we have a diagonal matrix. Diagonal matrix has only the diagonal as numbers. Everything else is 0. So in the first 2 by 2 matrix, we have 1, 0, 0, 2 row-wise. So our diagonal is 1, 2. So if you highlight the diagonal, everything else in this matrix is 0. So this is a diagonal matrix. In the second example, we have row-wise 1, 0, 0. Second row 0, 3, 0. Third row 0, 0, 1. So if you look at the diagonal, we have 1, 3, 1. So if you highlight 1, 3, 1, every other number you see is 0. So it's a 3 by 3 diagonal matrix. Lastly, we have a matrix 3 by 3 row-wise 0, 0, 0. Second row 0, 2, 0. Third row 0, 0, 0. So if you highlight your diagonal, we have 0, 2, 0. So besides this diagonal, if you observe every other number, they are 0. So this is also a diagonal matrix. A diagonal matrix may have a 0, but it cannot have entire 0. Okay. In a diagonal matrix, they're both upper triangular and lower triangular. If you need to use it as an upper triangular, we use it as upper triangular. But if you need to use it as a lower triangular, you can also use it as a lower triangular. So a diagonal matrix is both. Then our last concept here is the unit triangular matrix. Unit triangular matrix, they have specifically number 1 in the diagonal. And then if it's a lower triangular, then below the diagonal, we have all the non-zero matrix, all the non-zero number, and above the diagonal, all the zero numbers. Similarly, we may have unit upper triangular matrix. It means all the entry on the diagonal is 1, and above all the ones, we have non-zero numbers. You may have a couple zeros, but not everything is 0. So below the diagonal, every single number you see, they have to be 0 for an unit upper triangular matrix. It's called unit because our diagonal is unit. It has only 1 unit. Any questions so far? No? Okay, then the last concept of this section, triangular factorization. If a square matrix A, or you may have non-square matrix, it doesn't matter, can be reduced to an upper triangular form using only row operation 3, then it is possible to represent the reduction process in terms of a matrix factorization. Basically, they are saying if you can reduce a square matrix only by using row operation 3. Row operation 3 means multiply one row by a non-zero constant and add with another row. Using this operation using only this operation, if we can reduce it down, then all those processes to reduce them down, we can, for every process, we can find a matrix. And then our A matrix will be the product of all those reduction matrices. Specifically, we like to divide our A matrix into 2 pieces. One is lower triangular, one is upper triangular. So we represent L for lower triangular and U for upper triangular. So we can reduce our A matrix, or we can divide our A matrix into 2 pieces. One is lower triangle L and one is upper triangle U, 2 matrices. So when you multiply L and U, you get back the A matrix, the original A matrix. That's why this form A equals LU is called the triangular factorization of matrix A. Now you may wonder, why do we care? Well, we care because it's a very useful way of doing elimination process. You may not remember the elimination process. In elimination process, we eliminate one variable every step. This is called elimination. So it's a good way to represent the elimination process. Also, we will find this particularly useful when you study computer methods for solving linear systems. Many of the major topics in linear algebra can be viewed in terms of matrix factorization. So if you take linear algebra, or in future, if you do anything with linear algebra, this factorization will be very helpful. So the 2 matrices you're talking about, the L and U, they actually have their specific characteristic. The L matrix, the lower matrix, it has to be unit lower matrix. It means we have to have diagonal consist of 1, and all the numbers below the diagonal, they're non-zero. And then the rest is 0. So its characteristic is the unit. the diagonal is strictly consists of one, only one. And then the upper triangular matrix, the U, it's the upper triangular matrix. And in this upper triangular matrix, our diagonal consists of the original diagonal for A, and below A, we get all the zeros. This is the characteristic. The lower matrix is a lower triangular, which is unit lower triangular, and upper triangular has the diagonal same as the original A matrix. Now let's do an example. But before that, what we do is we apply only one operation on every row. And that operation is whatever row you are trying to change, it keep that row and multiply by and subtract or add by multiples of the other row. For example, if you try to change row 2 1, means row 2 column 1, you're going to do row 2 minus some type of constant times row 1. So whatever position we have, first you have to keep that position, keep that row, and you have to subtract the position of the column. So 2 1 means row 2 minus row 1, and row 1 will be multiplied by a constant. And let's say you want to change row 3 1. So it means you keep your row 3 and you subtract row 1, but you multiply row 1 by some constant if it's needed. If it's not needed, you just skip it. But if it's needed to multiply by some constant, you have to multiply it. So it's an easy process. Keep your row, and then depending on what number you have in the column, you subtract that row with that number. And no, addition is subtraction, depending on what you need. Okay, so here we have A as row wise 2 4 2, 1 5 2, 4 negative 1 9. So we are going to break this into two pieces. One is L and one is R. Sorry, not R, U, upper. So L matrix is strictly unique. Not unique, sorry, unit. So it's 1 0 0, 1 0 and 1. So this is fixed, okay? We cannot change them. It's 1 0 0 on the first row, and then some number here, and then 1 0 second row, and then two numbers, whatever number we need, we're going to find them, and then the last entry should be 1. So this is what we have. That means we only need to replace 3 positions. Position 2 1, 3 1, and 3 2. For upper triangular, it has the same diagonal as the original one. So original one has diagonal 2 5 9. So we are going to have 2 5 9 diagonal, and it's upper. So we need to fill out the position first row, second column, and third column, and then second row, second column, second row, third column. These 3 positions need to be filled out, and the rest will be 0 0 0. So you keep the position of the diagonal from the original matrix. Below the diagonal, you have to make 3 zeros. So we have 0 in 1 position, 0 in 4 position, and we want 0 in negative 1 position. 1 needs to be 0, 4 needs to be 0, and negative 1 needs to be 0. Okay? So what we do is this. We create the U matrix. So we convert the A matrix into U matrix. And then whatever process we need to use, or whatever constant we need to multiply by, those constant will go in the lower matrix. Okay. So this example is already worked out, so you can take a look at it later. let's do one example together. No, actually, let's do it together because the second example is a little bit fraction wise, and you may get lost in the fraction wise. So let's do it here instead of going over the question. Let's do it together. So we have, let me write this down. We have a matrix as 2, 4, 2 row wise, 1, 5, 2 row wise, 4, negative 1, 9 row wise. So our goal is to convert this into two matrices. The L matrix will have one lower triangular. So 1, 0, 0, and then 1, 0, and then 1. This is our lower matrix. So we need to find the second position, first position, and the second position. So these three places are missing. We're going to fill them out. To fill them out, we are going to create our upper matrix, which has the same diagonal as the original A matrix. So let's fill that out. We have 1, 5, 9, and it's upper, so we're going to have numbers here, here, and here. And below that, we're going to have 0, 0, and 0. The upper matrix, which we're going to have, has column wise 1, 0, 0. Second column is some number 5, 0. Third column, first two numbers we don't know, but the last number is 9. Okay. So how are you going to do it? Isn't this supposed to be 2? Yes, 2, 2. My bad, sorry. Thank you for catching that. 259. So 2, 0, 0, don't know, 5, 0, don't know, 9. Now, our goal is to convert this 1 into 0. So the position for the 1 is row 2, 1, right? It's the second row, first column. So to get rid of that 1 and make it 0, we need to do row 2 minus row 1. But then you have to multiply row 1 by some constant. So what do you need to multiply the row 1 by? So that the 1 position, 1 becomes 0. So let's write it down here. We have row 2 is 1, 5, 2. And we need to multiply by something so that we get 0 here, 5 here. And then we don't know, 1/2. Good. So you need to divide the first row by 2 or multiply by 1/2. So 2 divided by 2 is 1. 4 divided by 2 is 2. And we have 2 divided by 2 is 1. And then we need to subtract. Minus, minus, minus. So we get 0, 3, 2. So 0, 3, 1. What I'm saying. 0, 3, 1. Oh, sorry, my bad. They don't get the same number because when we do the reduction, they change. So this one we are not sure. What we definitely sure is the first position. The first position stays same. And then the second and third position on the diagonal, they actually change. We don't know, but we don't care because our main goal is to get 3 zeros below the diagonal. So whatever number we have the diagonal, they just come automatically. So we have 0, 3, and 1 here. Oh, and first row stays same. 2, 4, 2. First row stays same in the upper triangular. The second row, we just turn into 0, 3, 1. And then now we need to convert this 4 in the original A into 0. So the position for the 4 is row 3, column 1. So Ashif is giving me the answer. It's row 3 minus 2, row 1. Perfect. So if you want to see the work, our row 3 is 4, negative 1, 9. And twice row 1 is 2 times 2, 4, 4 times 2, 8, 2 times 2, 4. And when you subtract, all the sign changes. So we get 0, negative 9, 5. And so we have, let's write it down. So this is A2. We have 2, 4, 2, 0, 3, 1, and 0, negative 9, 5. I cannot write U yet because U has 0 in this position. The negative 9 has to be 0. So negative 9 has a position, what position? It's third row, second column. So 3, 2. Third row, second column. That means we are going to do row 3 minus row 2. And you have to multiply row 2 by some constant if it's needed. So let me do it here. Row 3, 2 means row 3 minus row 2. And let me do the work here. Oops. Our row 3 is 0, negative 9 first, 5. And we have row 2 is 0, 3, 1. What can you multiply row 3 by so that the result becomes 0, 0, and some number? Multiply by 3. Good. So multiply by 3 here. So we get 3 times 0, 0. 3 times 3, 9. 3 times 1, 3. So the answer is 0, 0. 5 plus 3 is 8. The last line is 0, 0, 8. So we found our upper triangle. Let me clear everything out so that you can see. We have 2, 0, 0, 4, 3, 0, 2, 1, 8. This is our upper triangular. And now you may wonder, well, how do you find the lower triangular? Once you get upper triangular, you get the lower triangular automatically. You know how? Look at this cool thing. The position, this position, when you convert 1 into 0, we needed to multiply by negative 1/2, right? We converted 1 in A to turn into 0. We multiplied that 1 by negative 1/2. So the lower triangular matrix will get the same number with opposite sign, which is positive 1/2. Now the 4 in A matrix, so is the 3, 1 position. To get to the 3, 1 position, we multiplied by negative 2. So in lower triangle, in 3, 2 position, in 3, 1 position, we are going to have positive 2. It's the same constant, not the constant, same coefficient with opposite sign. And then to get rid of the negative 1, which is 3, 2 position, we needed to multiply by negative 3. That means that 3, 2 position in the lower triangular will be positive 3. Sorry, we actually didn't multiply by negative 3. We multiplied by positive 3. because we have -9. So we added all of these. So since we multiplied by +3, so we have to put -3 here. Okay. So whatever you multiply by, whatever constant you multiply by to get rid of the number in that position, the exact same position get the same number. So at the end, our A matrix is a combination of L matrix times U matrix. And the combination means multiplication. So that means if you multiply the L matrix with the U matrix, you're supposed to get the M matrix back. So you have to verify. Most of the time you should verify. So in the exam, I'm going to give you points for verification. First, you're going to find LU matrix and then multiply them to get the matrix. So here, if you multiply 100 by 200, we're left with 1 times 2, which is 2, the first position. Then the first row, second column is 430. So 1 times 4 is 4, and the rest is 0. You get 4 here. The third row is 218, and you're multiplying by 100. So the 0 cancel out, you get only 2, which is the third position in the first row. And with the same thing, you have 1/2 times 2, which is 1, and the rest 2 are 0. So you see you get 1 here. Then 1/2 10 times 430. 1/2 of 4 is 2, plus 3 is 5. So we have 5 in the second position of the second column. Then similarly, you go the other way around. 1/2 10 and 218. The first two position is 1/2 of 2 is 1. So 1 plus 1 is 2. You get 2 here. So you need to multiply L and U and see if you get A. If you do get A, that means you L and U are correct. If you don't get A, that means something is wrong. So you have to go back and check where did you make the mistake. Okay. So give me 5 more minutes. We are going to do this example in our next class. Okay. And then I'm going to show you another way of finding this. So if you find this L and U is confusing, then there is actually another way of finding L and U matrix. So you know the position. In the L matrix, we have column 1, 1, 1, and above the 1, 1, 1, all of them are 0. That means we left it 3 positions. Let's fill them out with variables. Let's say the first row, the first column and the second row is X. First column, third row is Y. And second row, second column, third row is Z. So you have X, Y, Z unknown in the lower matrix. And in the upper matrix, we don't know what will be the diagonal. The A is whatever we have in the original matrix. That is known, okay? A is already known. But then what is B, what is C, and what is D, E, F, we don't know them. So we can just find them. So here for this one, you multiply A and L and U. So this is L, this is U. So you have 1 times A is A, and you put this as the first position. So the product of the first row, first column should be the first position in the A matrix. Then the product of the first row and second column on the U should be the second position of your A matrix. So 1 times D is D, and then the rest is 0. So D is 0 here. Then the first row, third column, the 2 0 cancel out, so you left with F. So F is the first position on the third column in your A matrix, which is 1. So here, basically, you're doing system of equations to find out what do you have. For example, in the next column, we have X10, and in the row wise, we have A00. So the 0 cancel out, you left with only a and x. So ax is the second position on the second column, second position on the first column, which is 6. But you already know your a is 3. So your x is half of 3, which is 2. And then you do similarly. You take the second row. Where is this? You take the second row and you go to the second column. So in the second column, you have dx plus 1b equals the second position in the matrix, which is 1. But you already know your x and you already know your d. Your d is 0, so your b is actually 1. And then you have the third row, third column, x times f, which is xf, plus e times 1, which is e, plus 0 times c, which is 0, equals the third position 1. But your x is 2 and your f is 1. So this is e equals 1 minus xf, which is 2, which is negative 1. So you find out each one of the variable this way, and then you just place them in the order. X, Y, Z goes in the left lower triangular matrix, and then A, B, C, D, E, F goes in the upper triangular matrix. And that's it, you know. Okay, any question? Try to do the homework, and if you find confusing, we're going to discuss them more tomorrow. But tomorrow my plan is to, so we're done with this section. My plan is to go over this question. So we're going to start with this question, and then we're going to start chapter 2. Any question? Now my throat is hurting after talking for an hour. Any question? Any comments? Concern? Complaint? Nothing yet? Okay then. Concern about me? Thank you so much, Yvonne. I really appreciate it. And thank you so much, all 17 of you, for being here for 10 more minutes. Thank you so much. Thank you, Shibu. So have a good night, everyone. See you all tomorrow again, online. Thank you, Alvin. Thank you, Joseph. Bye, Kailun. Thank you, Wenchuan. Thank you, Shane. I understand. No, don't worry. Have a good night.
Night.
Good night.